So last lab we talked about permeability, and I've sent an email for everyone. I uploaded some data that you can use in the report, and it's going to be due the following week. And you just have to include that data in your lab report, and that's pretty much it, and the general procedure and introduction and everything that was posted in the syllabus that you need to have in each lab report. Today, we are going to talk about the direct shear test. So this test, this is the ASTM standard here. This is for what is known as a drain test that is performed on granule material, so sands and gravels. And we'll go into what is drained and versus undrained. Basically, this is a shear test, so you have a shear force right here being applied to a soil sample. And you have the soil sample in here, and you'll have like the permeability test. You'll have like a permeable rock here and a permeable rock on this side. And what you will do is you'll apply a normal stress or a normal load to the sample, and simultaneously you'll apply a shear force from this direction, and you will shear the sample. So you will cause the sample to fail. While you're doing this test, you are recording a couple of measurements: a vertical measurement to indicate the vertical movement of the soil sample. Will the soil sample in here compress, or will it dilate, increase in volume as it's being sheared? And you have also a lateral displacement, so you will record the strains in the lateral direction as you're failing the sample. And from this, what we want to obtain is a shear strength. So how much this material, how much shear force can you apply to this material before it fails? And this is very important in all geotechnical engineering design and testing. So when we're talking about lateral pressures, you'll see that in the lecture, slope stability or bearing capacity, you always need to get a value of the shear strength of the soil, its ability to resist that horizontal load. And this is just some background for it. So it's an ideal model, and we mentioned this at the first class, that in soil, you're trying to simplify the problem so you don't have too many unknown or non-linear relationships that you cannot quantify. So this is a simplified model. It's a 1D. By what I mean by model, I mean by the more Coulomb failure model, which we'll see in this lecture. So we said that the strength comes from intergranule friction and interlocking. And we will see in this test that these two frictions will play an important role in the shear strength of the soil. And that depends on a couple of things. It depends on the shape and angularity of the particles themselves, the initial voids ratio, so how compacted or how loose is the material that you're starting with, and the degree of over-consolidation, which we'll talk about in detail when we get to consolidation, which is the next lab. So for the shear strength of soils, again, this is just reiterating what I said. It's resistance to shear, to shearing stresses, and it's a measure of the soil's ability to resist motion or movement or slippage in relation to an applied force. So this is the shear strength of the soil. which depends on the interparticle friction, again, like we said, and the interlocking between the particles or the friction between particles themselves. So this model basically it has two main sources. In granule soils, like the soils we're talking about right now, the only thing we are interested in is the frictional resistance. So this component. And what's wrong with this? Okay. So the frictional resistance. Cohesion is for clays and silts, and that's depending on electrochemical or electrostatic forces between the clay particles, because they have a charge, and if there's water around them, it has a charge, and that's cohesion. So this is where the soil derives its strength from. This model is simply based on statics. So if we imagine that our soil is a block like this, and we're applying a force to it, and this is resting on a table, then you have a weight of the box, you have a reaction. Let me try to. Still can see it, right? So it's just based on basically if you have a force here, you have a weight here, and this is sitting on a table, and then you will have a reaction force, and you'll have here frictional resistance. And it's very simple. This frictional resistance we know from statics. It's frictional resistance is equal to mu multiplied by the reaction force. And then in soil, so like it's just imagine that the block is basically two soil particles, like one table, one is the block. This is the basic theory behind it. And then what's happening is if I keep increasing this F at a certain time, this block is going to begin to move, and that's the limiting force. And if we just make a vector relation between these forces, here you will have the reaction force. Here you will have mu times r, and here you have theta. And this theta is, or if we want to find this theta, so we'll say like tan theta is equal to mu r divided by r. And we can cancel these out, and then what we'll have is mu is equal to tan theta. And from that, we can go back to this frictional resistance, and we can substitute this this mu in there. So it will be tan theta multiplied by r. And that's equal to the limiting friction between the grains, or in this case, between the boxes, which is the same thing. This is what the model is based on. And we know that stress is equal to force over area. And with that, if we divide everything here by area, then you will have a shear stress, which is equal to R over A, and that's going to be equal to the normal force multiplied by tan theta. And this is basically the Moore column failure that is concerned with frictional resistance. That's just, it's very simple. It's based on statics, and that's what we use, and that's the failure criteria that we use. And we'll use this throughout. So you will use this in when we do triaxial testing, the Moore column failure criteria. You'll use it in this test, and you use it in mechanics of material, and it's a very simple model. Now, why do we do this test, or why this test is important? Because we have shear failures. So failures usually happen for two reasons. One reason is that the laboratory approximated shear strength is less than the shear stress that will be applied in the field. So basically, we calculate a value and we use it, but what we experience in the field is a lot more than that shear strength that we measured in the lab, so things fail. Or we use a wrong we perform the test incorrectly, so we have wrong values of shear strength. We have high values while really it's very low, and or the shear stresses being applied in the field will be more, or we will have a problem in the data analysis. So when we're looking at our data, we might get a strength that is not the required strength, and this happened many times. Here, it happened in Canada for this grain elevator. Now, I can send you this case study if you are interested. And another type of shear failure is liquefaction. And liquefaction is, it's not, we don't really have to worry about it in Louisiana, in this region, in the Gulf region. They worry about it in California because it happens in granule soils, basically granule soils. With increase in pore pressures, they lose their strength completely. So it would be something like this is the ground level and this is a house, and here you have soil, and in between the soil you have water. So you have water in here. With some form of cyclic loading, this water will basically surround the whole soil and it'll become like a liquid, and this building will sink in. And that's just, I'm being very simple in explaining liquefaction. And it's a very important thing for people in Japan, people in California, because they have a lot of these granule soils. We have to worry about water, which is very bad as well when it comes to soils. This is the Moore column failure criteria. So basically, this is the component, that the frictional component that we talked about, and this is C, the cohesion that we talked about. And by the end of the slab, we will be able to do a shear strength plot with normal stress, and we can see this failure line, where this failure line is. And basically, when you're trying to design, you want to stay away from this failure line as much as possible. And this is the internal angle of friction for the soil. So we always want to, when we're talking about shear, we always care about the effective, meaning we have to deduct the importance of water. If you know, I'm sure by now everybody knows in the class effective stress, which means we take out the effect of water. And that's important because we're talking about shear, and we know that shear cannot take a shearing stress. You know, it deforms under shear. So we ignore we don't want the effect of water to be there, because that's fake. Water cannot resist shear. It deforms continuously. And that's basically it for the Moore column failure criteria, and we'll go back to this. For the direct shear test itself, what we have here, we talked about, this is the box, and inside the box we'll have sand granule material, or we can, they say, I mean, don't use direct shear, or not don't use, it's not very good to use direct shear testing cohesive material, but you can still do it if you control the shearing rate. So the rate of this arm moving, if you slow it down enough, you can get accurate values of shear strength with the direct shear test for cohesive soils. For our lab purposes, we're just going to say that this is gravel and sand in this box here, inside this box. And you have these two plastic screws that will be removed before the test can start. It's only for making sure that everything is aligned, and then you need to remove them so the sample can move left and right and can fail. And you have these dial gauges, and the one that we have at the University of New Orleans, we have a transducer, so it's not a dial gauge like this, and we don't have to worry about some corrections. And for a better view, this is basically what's going on. You're applying a normal load at the beginning of the test, and then you are shearing the sample, and this is the surface of sliding that is you're failing the sample across. Some people who don't like this test say they don't like this test because we know that soil has infinite lines of failure or areas of failure, surfaces that can fail across. So when you're doing a shear box test, you're limiting the soil to fail in a certain a plane. So that's why some people don't really like this test, but nevertheless it's accurate and it's been used many times in design. And I think we can take a look at this video that Charleston University
This is a tutorial for the direct.
So basically this is the Shearbox that you use. This is the jig that you can apply the normal stress to the sample with. So you start with like 4 kilos, then 8 kilos, then 16 kilograms on the sample, and that's just a normal stress. And then this is the mechanical equipment that will create the shearing force, and then that box will slide. You have these transducers that record the vertical displacement, horizontal displacement, and you'll repeat the test, but you need to ensure that, for example, this is, so this is the gauge. This is the soil sample. He'll take a weight because you want to calculate the dry density that's in here. So he'll take the weight of the sand that he's putting in. You can get a caliper and measure the dimensions of this box. So by the way, this box can be square or it can be a circle. In the video, it's a square. It can be also a circle. You'll measure the dimensions of it, length, width, and height. Then you can have the volume, you have the weight, you can calculate a dry density. What he's doing here is making sure that the surface is flat, and if there's excess material, he's removing it. These are the plates that will allow the shearing to happen across the two planes with confinement. So with that normal stress, confining stress that's being applied to it. And basically he'll place it in here, and that's the transducer in the horizontal direction. This is the jig that applies the load. So the load goes from this bar to this steel ball, then into the sample, and that's the displacement or strain changing with the load. And that's the normal stress. That's how the normal stress is being applied. So basically first it's applied at the bottom of this jig, and then through this steel pin, it'll be transferred onto the sample. With that, there'll be some shear applied, and you'll fail the sample. Then you'll prepare a new sample with you have to try to hit the same dry density, so you have something to compare about. You don't want to compare dense sand to loose sand, and so we'll talk about this in a little bit. You can calculate I'll show you the calculations with the slides. So basically this is what the direct shear test is very quickly. Does anybody has any questions about what we went through so far? Okay. So this is the displacement. This is the shear applied shear force. No, this is the applied shear force, and this is the reaction by the sample itself to failure. That's the surface, and with that you can calculate the strain, or you can calculate the shearing force. Basically, these two calculations are from mechanics materials. This is the normal, and this is the cross-sectional area. So in our case, we have a box, we have the length, the width, and the height of the box, and we need the area in this calculation, so we'll have that. And we know what normal stress we are applying. For the shear, we have the load applied to the side of the shear box, or to the one part of the shear box. So one is the top, and this one is the one that stays stationary. And from that, we can calculate the shear strength. And this is the area parallel to the cross section where that side shear force is being applied. This is a picture of the equipment. Again, here we have some gravel. We have those stones, porous stones that we talked about. You can put some filters so you don't allow the material to mix up together. These are the drainage holes. So basically, this chamber it will be filled with water. So as you apply, you want the water to move out of the gravel or the sand, or even in an undrained situation where you're testing cohesive soils. And those are the two screws that you need to remove before you start the test. Otherwise, they'll break because they're in that shear line, this line. And after you place it, you place the load jig on top. You align the screws. These are the gap screws. You ensure that all of these are removed before the start of the test, and then you can apply a specific strain rate to that. Now, the first thing you need to get is this is the volume, or the volume changes if we start with a dense sand. So if we start with a dense sand, then this is or loose sand. This is what we are. This is the shear stress that we will see, and this is the horizontal displacement that we will see. So basically, when you start with dense soil, what's happening is all of these soil particles are packed like tightly to each other. So the only way that they can move once you start shearing them is up. And that's why you have this, you see here, this volume change during shearing. For dense, it starts to dilate and then it tapers off at some residual volume. Or if you are having loose soils, so if it's loose, then you start shearing, where this is going to move. They're just going to get closer to each other and have more frictional resistance. But in terms of volume change, they're only going to contract. They're going to decrease in volume. And then also they'll taper off at some applied shear stress. Now, this is the horizontal displacement. And you see here in dense sand, it'll increase to a peak. Basically here in this area, what you're trying in this whole area, actually, what's going on in this area as you're applying it before you get to a peak shear stress, and that you'll see that through your data, is the interlocking part of the strength is being overcome. So once you overcome it, sorry. So once you overcome it, then this is here the what is known as the residual strength or long-term strength. And that's what sometimes in design, it depends on what kind of conditions you're having. Are you having short-term conditions where you will use peak strength, or you will have long-term conditions where you'll use the residual strength? So this whole initial time, it's just the strength of interlocking between the particles, and then this is where the behavior is purely frictional. For loose, we don't have a peak. We're gonna increase. They're gonna kind of move in a denser state. If there is water in between the particles, it's gonna go out, and then it will reach the same shear stress similar to the dense soil after a certain rate and a certain time of applied load on the sample. So back to when we said that this test was drained. Drained in geotech has nothing to do with how wet or dry your soil is. Drained means that the water can move in and out of the sample as soon as the load is applied. Meaning, like, let's say granule material, when you apply the load, water has enough time to move out of the soil sample almost simultaneously as the load is applied. However, you have to be careful. You cannot apply the load too fast, and then you will have something called apparent cohesion, which is like cohesion that isn't there. For example, in this case, we have this C, and this is in loose sands. Basically, when you're applying, when you're shearing the sands, at the start, the sand is trying to dilate or increase in volume. And because there's water around, it's saturated, then it's gonna try to pull water in, and then there's negative pore water pressures that will generate, and this will show a fake cohesion, if you will, that is not there. It's there right now, but after a certain period of time, it's gonna go away. But what I mean by it's there right now is there's water in between the soil. So that water, for our purposes, is incompressible. So it can take some of that load. And when the water goes away, then the whole load is felt just by the soil grains. And that's what we mean by drained. So it has nothing to do with wet or dry. It simply has to do with the water movement in and out of the soil. So basically, a saturated soil can be called a drained soil, because if water can move out or in the soil as soon as the load is applied, then it's drained. Undrained, there is no change in movement of water with the load being applied. So basically, when you apply the load, there's no change in the water coming in or out, and that's called an undrained test. And we'll talk more about undrained tests in the triaxial test, which I think it's our last lab, and we'll explain this more. But I just want you to understand that when I say drained or I say undrained, I'm not talking about whether the soil is dry or wet. I'm just describing the movement of water in the soil. And this becomes really important when you're trying to select which type of test to use based on what you're trying to calculate. Again, do you have any questions about what I just said? Okay. So the shear box inside diameter is 2.5 inches. This is the area. That's the shear box height, and we'll measure that with a caliper. We need the height of this porous stone because if we want to do any volume calculation, we just are interested in the volume of the sample. We don't care about the volume of the stone above the sample and below the sample. This is the soil volume, initial mass of soil in, and then the final mass. From that, you can calculate the soil density or dry density of the soil. And that's a very simple calculation. If you wanted to do a void ratio plot, that's also easily done because we have all the measurements that we need to calculate the void ratio. Volume of voids over volume of solids, I think. The volume of void of volume solids. Should remember that. Yes, so it's volume of voids over volume of solids. And with that, you can calculate the void ratio, and we'll have, or we can actually, we can use another relationship for that. We can use the specific gravity multiplied by unit weight of water divided by the dry unit weight minus 1, and that will give us also the void ratio. Here, there's a critical void ratio, and this critical void ratio, it's a void ratio for granular material at no change in volume will occur. So you see, even for dense or loose sand, after changing, after the void ratio decrease or increase, there's going to be critical value for both where there's no change in void ratio even after the application of a shearing stress and a normal stress to the sample. So for these we talked about these calculations. So these are the horizontal displacement, horizontal strain, and horizontal shear force, and the shear stress. And these are values that will be recorded. And this is the normal stress that we're applying. So this is almost 7 pounds per square inch. And with that, you can have a plot at this normal stress. And as you see, as you increase the normal stress, you will have an increase in the shear stress. And you can draw a best fit line. And in this best fit line, this is the slope, and this is the phi. And you can see here the y-intercept is 0, so cohesion is also 0. This is the normal, and this is tan phi. So basically, you can find for this particular soil what's the failure criteria, and with this failure criteria, you can proceed with your design.